Igor Mordatch to give a guest lecture on this topic. He's a research scientist at Google Brain, working in machine learning and robotics. Previously, he was a research scientist at OpenAI after completing his PhD at the University of Washington and postdoc here at Berkeley. So without further ado, we can go ahead and get started.
Yeah, thank you very much for the introduction. So I will continue. I will continue talking about the theme of optimization-based control. And previously, in just the last lecture, Pieter has talked about locally optimal control, and in particular making these distinctions between shooting and collocation methods. And earlier in the lectures, most of what we've talked about, we've primarily been looking at forward dynamics models, such as next state is some function of the previous state and your controls. And we looked at advanced methods for shooting classes of problems, like looked at LQR or differential dynamic programming. During the lecture today, we're going to look at direct collocation methods in more detail, both for optimizing open loop policies, open loop control sequences, and optimizing feedback policies. And we're also going to look at inverse dynamics models, where you can recover the controls from just sequences of states. And we're also going to look at advanced solution methods for optimization problems, similar to basically analogs of LQR and DDP for direct collocation. And then we're also going to look at optimization in the presence of contacts, and what are some of the challenges and possible solutions that can arise for that, which are like really ubiquitous in robotics settings. So let's get started with just trajectory optimization and direct collocation. Make sure we're on the same page. Let's say you have this problem where you have a system in some initial state, and you wanted to minimize or reach some goals, such as, for example, reaching the target. And we've looked in the past at forward shooting methods, where you directly optimize for a sequence of controls that, when rolled out with your forward dynamics function, result in some sequence of states. And you would like to then choose such control sequences that minimize some cost function, like reaching the goal. Right, so this is kind of like what we've seen. And the issue that Pieter has brought up last time is that this problem has very poor conditioning. Oh, and by the way, throughout the lecture, like if you have any questions, please feel free to ask me. We can be pretty informal here. But this problem has poor conditioning. So, for example, if you change the initial controls, that has very significant implications on the rest of your trajectory. And this can be seen more directly if you unpack this set of equations. You're basically chaining your forward dynamics function f multiple times. So it becomes, and any particular state at time t is dependent on all the controls leading up to it. So it becomes very, you basically accumulate sensitivity. The other issue that I don't think Pieter actually brought up is that you have very narrow feasible regions for these problems, because this dynamics function, you can think of it as an implicit hard constraint. Like all of your solutions have to satisfy, by construction, these forward dynamics. So that may result in very narrow feasible regions. So if this two-dimensional space is the space of all your possible trajectory sequences, the red region is all the trajectories that satisfy the dynamics equation that you see throughout trajectory. So if, for example, you're running your optimization and your initial guess for a trajectory is somewhere, you might have to take very roundabout paths throughout the optimization to reach the solution. As opposed to, for example, if this was, say, a soft constraint and not a hard constraint, you could see maybe the optimization could take much shorter paths to the solution. So it could, in the intermediate stages, break the laws of physics, have something that is not physically plausible or consistent, but then converge on a solution that is. And if you think that this is just like a pathological case or example, this actually does come up in practice quite often. So, for example, collision events that happen with real robots, or let's say you have a bipedal robot or some robot that starts standing, most of the sequences of controls you try will just lead to it falling down. And you're not going to be, that is all you will see, and you will not be able to make much progress there. It would be very hard. So these shooting methods are very prone into falling into local minima, and the solutions are very sensitive to the initial guesses of the controls that you choose. So you could ameliorate this somewhat by choosing initial guesses from demonstrations, or potentially doing a lot of randomization and trying a lot of trying basically random search for this. But there is an alternative, as we've seen from the last lecture. As opposed to optimizing for sequences of controls, what you can do is optimize directly for the sequences of states and controls, potentially. In the case that I will discuss throughout the lecture, we will actually be only directly optimizing for a trajectory of states as opposed to states and controls, where the controls can be recovered implicitly via the inverse dynamics function that for a pair of states will give us the control. So we don't need to have it as an explicit optimization variable. And in these settings, what you have is only the pairwise dependencies. And so you have good conditioning properties that changing, for example, x1 has the same effect as changing your optimization variable xt. It's not like some of the variables have disproportionately large effects on your cost function. The other advantage is that there's also no instability due to forward integration. So we've seen we typically need to take pretty short time steps in forward dynamics simulation because due to time discretization and explicit integrators like Euler integration, forward integration can quickly grow unstable. So we have to take very short time steps. We don't have such issues of instability due to forward integration here, which is nice. Yeah.
In the forward dynamics models, do you have to use an Euler integrator, or do you just use a higher order integrator?
Yes, so that is a game that you can play, and in fact, many physics simulators do try to have higher order integrators, like Unge-Kuda integrators, to try to solve some of these stability issues, but it's still, basically, this is equivalent to using implicit integrators, which are known to be actually not to go unstable. In fact, if anything, they actually dissipate energy rather than create energy. So this is basically the equivalent to using implicit integration methods. So these are some of the advantages around conditioning and stability. And the other one is, again, we can make this dynamics becomes an explicit rather than implicit constraint. And so it's a constraint that we impose explicitly rather than having it be satisfied by construction. And that allows us the freedom. It can also either be a hard constraint or it can be a soft constraint in the optimization. So the solutions potentially, the problem can potentially be less prone to local minima because we can just try infeasible states like I've discussed. So to summarize the differences, with forward shooting, we optimize over the controls, and the trajectory of states becomes implicit. Just because we roll out the controls, we see what states come out. But the dynamics equation, this F, is an implicit constraint that is always satisfied by construction. That is either a bad thing or a good thing. Like it's either a benefit or a burden. And direct collocation, you directly optimize over the states, whereas and controls and potentially constraint forces come out of it implicitly via the inverse dynamics. And this dynamics can be an explicit constraint, which can be made soft. And just to, I wanted to very briefly discuss that both of these settings that Pieter described in the last lecture and that I've just brought up are just special cases of more general collocation setup. So originally this was motivated by solving differential equations where you optimize, the parameters you're optimizing is some parameterization of your trajectory and controls. And you have various ways in how you can actually recover specific states, specific controls, and their time derivatives. And you basically test the satisfaction of dynamics only at specific points, which are called the collocation points. The reason I bring it up is that there's, in numerical methods literature, actually many other choices. We've just taken a very specific choice where theta is just the sequence of x's. But there can be other ways to parameterize trajectories. You can use like other bases, like polynomial basis of trajectories or Fourier basis. And there are many other choices of where you place these collocation points. We've just evenly spaced our time steps over a grid, which is fine, but you can potentially do some other like smarter or adaptive methods. So just want to bring up, and there's also, the other point is like, there's nothing sacred about basically choosing two neighboring states, basing your inverse dynamics on just two neighboring states. Like this is a local way to parameterize trajectories, but you could potentially have an inverse dynamics function that depends on many more states that is global. So that is just, yeah, wanted to have this small aside. Any questions, by the way? Before we jump into inverse dynamics, yeah.
Yeah, could you provide maybe some intuition about why you can make the dynamics soft in one case and in the other case making that constraint soft is wrong?
Well, you can't, in the shooting methods, you don't really have the option to make that constraint soft because that constraint is, by construction, is always satisfied. Like your x's are a function of your u's, so the relationship between them is just always satisfied by construction. Whereas in our case, like in the case that in the top formulation that Pieter brought up, you explicitly have the freedom to change your x's and your u's, and the relationship between them, that is an explicit constraint that you're satisfying. So that is not satisfied by construction. You have to explicitly enforce it. Does that make sense? Cool. Yeah.
How do we know that the inverse dynamics map exists, and does it need to be unique? Because there can be many control sequences which can be used.
That's right. Yes. And so the first question, does it exist? We will get back to that later. It need not exist. You might have some unfeasible, just there is no way to transition from one state to some other state. And in this case, as we will see, we can have, like, the inverse dynamics might have some residual, which I'll get back to later. So you will be able to get information like these pair of states is not possible. And also even like by how much, like the degree to which they are impossible. To your second question, is it unique? It doesn't, that is a tricky question. The way that physics simulators have been proposed and built is that you would always have a unique solution to this. But there are some generalizations where basically you might not have a unique solution. So there might be multiple controls that lead you to the same thing, and people typically like propose some ways to regularize or like some prior to put in such that we can always recover a unique solution. But that is sort of like a little bit fooling yourself. Because even like, for example, if I'm just like in a pose like this, you don't actually know how hard I'm pressing against the table right now, right? You just can't recover that from from the poses alone. And people basically propose ways to, like some regularization methods to like have a unique solution for this. But it's a little artificial, yeah.
Maybe you'll get into this later, but what are the pros and cons of the first method up top and the second method, where the first method is states and actions, and the second one is just over states?
Yeah, I will get to that a little bit later, but in general, if you have the power to recover the states via the inverse dynamics, as I will discuss next, that's less variables for you to optimize. And yeah, this is a choice that you can make, and some of the work has done it in one way. We will actually see some examples, or you can do it in the other way. So there's, yeah, like no, it's been done in both ways. But I generally, like the personal feeling, and I think there is a body of work that says the second way is kind of favorable if you do have access to inverse dynamics function, you can use it. The problem is you might not always have that. And in that case, you would have to use the top method. But if you do have it, so maybe let's now discuss like what is this inverse dynamics function and unpack that a little bit more. So again, it describes what are the controls and forces you apply when you transition, like you have specifically state x of t and xt plus 1, and then what are the controls and forces. One way you can choose to go about finding this function is just be learning it from data. So I think like Pieter has been talking about learning methods. So what you can do is just try to gather a data set where you apply a bunch of controls. You look at two pairwise, like two neighboring states. You try to see what is the control that made you transition from that state to the next, and use your favorite function approximator, like a neural network, to try to learn a mapping from that input to those outputs. That is definitely a way that you can go, but for rigid multibody dynamics, we can do better if we know the system parameters. And so we'll go into this case right now, which I think is useful. Even if you're going to be using learning, it's useful to see what under the hood the physics simulator, what the ground truth really of physics simulation is, and what is the structure of those equations, so that even if you're learning it, you can maybe incorporate some of your knowledge of this structure into your learning methods. So let's go into rigid multibody dynamics. And in this case, the state x of t, we're going to include in it all the degrees of freedom of our robot. Let's say all the joint angles, and for the root, for example, like root position and root orientation. And we can calculate velocities and accelerations of these degrees of freedom just via finite difference in our case, if it's just a for our case. So a particular u now depends on the state at that point in time and the state before and after it. And the way that we can recover these controls is basically by generalizing f equals ma. So for example, if you had your equations of motion like f equals ma, you knew acceleration because you have access to the trajectories, you knew the mass, you can just, like, then you know what was the force that was applied. Now, in the rigid multibody dynamics, it's a little bit, that equation gets a little bit more complicated, but it's still the same idea, where you have more generalized mass terms and these specific Coriolis terms that depend on velocities. And on the other side, basically on the force side of the equation, you have your controls, which can be modulated. I believe you've seen it in the LQR lecture. They can be modulated by specific matrix, which basically can say that, well, there are some degrees of freedom I can control with my U's, but there are some other degrees of freedom. For example, like my root position, there's no muscle actuations I can apply to like move my root globally. Right, so this B reflects that constraint. And we also have some constraint forces multiplied by transformed by their Jacobian. And these would be, say, the contact forces that are applied, or if there's any joint limits, the forces that prevent your joint limits. So I've gone over this in just like very, very superficial high level. If this is something that's interesting to you, I would suggest an excellent treatment of this is given in Springer Handbook of Robotics in chapters 2 and 3. And there's another which talks about, unpacks this equation and all these terms, how to calculate them. Doesn't talk too much about contact. And if you want to understand contact, I think Analytical Dynamics: A New Approach is also a really short, concise, great book on the subject that talks more about these equations with contact. Yeah?
For the constraint forces, how do you deal with the, say, the friction change directions?
Yeah, so something that do you mean like frictional constraints due to friction? Yeah, this is something that I actually, for brevity, haven't mentioned. Like the variables f have constraints also on themselves, like they have to lie. The friction is expressed as a cone constraint, so f needs to lie within some cone, and there's also a complementarity constraint between positions and forces. But I would really don't want to go into the details of those, but yeah, there are some, much like there are constraints on Q's, like joint limits, for example. There might be some boundary constraints. So, but at the high level, then what you have out of your inverse, with your inverse dynamics function, you basically try to solve this equation. You have all of your Q's and their derivatives, and you can solve for the F's and the U's that satisfy this equation. And that is how you can recover the controls and the contact forces. And if it's not possible, like you've asked, if it's actually not possible, there's no sequences of, there's no Q's that actually make this equation hold, you can also, like the minimum of this equation is going to be your inverse dynamics residual. So this function R will tell you the degree to which these two states are transition between these states is impossible. And I should say, like, these equations can be solved either numerically or analytically, so there are closed form solutions to solving these equations. And this is, by the way, like, this is not just for direct collocation methods. Like, your favorite physics simulator is doing this, is solving this problem under the hood anyways, except for forward dynamics, you know the Q's, so you plug in, you know the Q and the velocities, you plug in your controls U, and you get accelerations out of it, but it's solving exactly the same problem. So this needs to be done anyways, or it's being done anyways. So maybe we can go over a simple example for just a 2D particle. Let's say your equations of motion, your F equals ma, is just you have some controls and you have some external force, G, like gravity. So the inverse dynamics function, if we were just to plug in our finite difference approximation, is going to give us that there is this form for u that depends on the x's. And let's say we're just trying to minimize, let's say our cost is, I just want my state x to be small. That's just for an example. And our initial state, it starts at 0. We know that our system parameter is m, and our external forces. The unknowns we're going to be solving for is the rest of the trajectory after the initial state. And the solution could just be basically the state continuing to be at 0. The implicit controls we can recover is g, so it's kind of like, can say the controls were applied were directly opposing the gravity. In the other example, for example, if we want to minimize controls instead, so basically effort, we don't want to apply any controls. We're going to see the sequence of states that is basically free-falling motion, and the implicit controls are going to be 0. So we can basically get trajectories that satisfy dynamic set of optimization. So now I'm going to talk about how we actually solve these methods numerically. But before that, any more questions? Cool. So numerical solution methods, the first thought really is, I believe you've looked at TensorFlow or Torch or various other like machine learning frameworks, like automatic differentiation frameworks. And so the first thought is, well, this looks like a graph. Why don't we just set up a graph in TensorFlow and try to optimize through it with gradient descent? And that actually would not be a terrible idea. This would be a sensible thing to do. But we saw from previous lectures that for shooting methods, we could do better. We had something that took advantage of higher order derivatives, and basically was like an equivalent of second order methods. We saw LQR, we saw differential dynamic programming. So can we do something similar, apply a second order optimization method for these direct collocation problems? And why would you want to do that? So Pieter gave examples that with second order, you have faster convergence rates, and residuals tend to be a lot smaller. You saw the plots of that from lecture 6. The intuition, for me personally, is that what you're trying to do is you're trying to solve a simultaneous system of simultaneous constraints that all are overlapping. And if you were doing it with first order methods like gradient descent, you could say, well, I'm going to try to changing my variable, but if you make one change in your variable, you're going to satisfy one constraint. You're going to violate another constraint. And so you're always going to be like playing this game of catch-up. Whereas we know that second order methods or linear system solvers are very, very good at satisfying multiple constraints simultaneously. So why don't we just take advantage of that? And in practice, second order methods do tend to be very important for getting these collocation methods to work. Something that considers simultaneously changing multiple variables. On some problems, it takes you from, second order methods take between like 10 to 100 iterations, whereas first order takes like between 1,000 to 10,000 iterations, and you're still getting like residuals that are not satisfied. So I think it tends to be actually more important than for shooting methods to apply this. So one particular method you can consider is the Gauss-Newton method, which is very similar to natural gradient, or the idea of natural gradient method that was proposed in lecture 6, where if we had this total trajectory cost that depended on some features. So this phi includes all the features we can think of, like this, like our controls, our inverse dynamics residual, maybe other features like end effector positions, basically anything we want to put a cost on. And if we look at the gradient and the Hessian, well, the gradient looks pretty straightforward. The Hessian, and by the way, in case you haven't seen this notation, like c sub x means the derivative of c with respect to x, and like cxx means like the second derivative of c with respect to x. So this is these like subnotation. This is just derivatives. And if you were to unpack this second order term, what you would see is it's something that basically depends on the first derivative of your features, and another term that depends on the second derivative of your features phi. And it's this term, the second term, that actually could be quite tricky to calculate. So if it's like inverse dynamics residuals, getting a Hessian of that actually could be quite tricky in practice, whereas just getting the first derivative of it could be done with, say, finite difference or other types of approximate methods. So the game you essentially could be playing, whereas like we're going to be assuming that our costs C are going to be something analytical so that we can get the first and second derivative of c can be calculated very easily. Let's say it's like a quadratic. So like a case might be if I want my arm end effector or my robot's end effector to go to a particular location, we might put the end effector position into phi, its coordinates, and c might just be like a quadratic between the end effector position and the target. So it allows us basically, we have the freedom, what terms, like what do we put in the c, what do we put in the phi? And ideally, in the phi, we want to put things that are hard to differentiate, and c is something that's easy to differentiate. And basically then what we can do is, what happens in practice is we can drop this term and just have this truncated approximation to the Hessian, which is kind of called the Gauss-Newton method. And so we can find solutions just by basically iterating Gauss-Newton steps. In practice, you can use, for stability, a damped Hessian, and I think Pieter talked about this in lecture 6, I think, as well. And so I think it would be very instructive maybe on your own time. What you can do is take a look at the relationship of these equations that I've proposed, and the natural gradient that was covered in lecture, and it's kind of the same intuition of dropping terms. So, but then the question is, we have this Hessian that we form, and it's the size of your state space times the number of time steps, times the number of collocation steps squared. Do we actually have to, and this number can be quite large, do we have to invert it at every iteration? And the answer is actually, luckily for us, no. Because if you look at the structure of the Hessian, because the dependencies between, like on the constraints are only local, the Hessian ends up being block sparse. And you can just use like your favorite out-of-the-box sparse linear system solver to solve this. Like so, Python's call actually works really great. You can do better, but this is already pretty great. And there's many other methods from numerical methods literature that you can apply to this problem, like multi-grid methods or various spectral methods that can speed this up. And you can also pose this as constrained optimization as well, so where your dynamics can be made hard constraints. We'll see an example of this later as well. So maybe before we get into Contact, do you all want to take a short break? Just take like 5 minutes, since usually, and if there's any questions. We're just going to talk about Contact. Yeah, maybe like for 5 minutes, take a break. I'm going to talk about Contact and policy learning.
Sorry, I kind of missed it. What is the dimension of the Hessian you mentioned?
It's x times t squared. So the size of your state, or sorry.
So this is the size of the state, and that's the time steps you have, right?
Yeah, so it's number of time steps squared.
Oh, I see.
Or, well, it's the size of the Hessian is like, it's a matrix of these dimensions.
Okay, so that will be, wait, let me go through this. So you have a number of states. This is your time span, and in each of them you have, say 60 degrees of freedom, so 6 of them time span.
Yeah.
And then, I see.
Yeah, so if your t is like typically like 50 to 100 time steps, yeah, you're like, as you say, 6,
yeah.
It's like 600 times 600 matrix,
okay,
which
yeah,
is,
thank you.
yeah.
Maybe a related question, the C matrix that blocks Mars, is it usually just a lot of 1 multiplied by the content for the
It tends to be, so not quite, it does have this form, but these, so the band of this, the bandwidth of this matrix is your size of your state space times 3. So because it's like relating with these.
Yeah. And if you go maybe like one.
But it's not like ones or zeros. Like there are specific like coefficients that are like all just like they're not ones or zeros.
Okay. Because I thought that most of the coefficient would just be coming from the time step integration. Like 1 minus 0.
That is how you would calculate. Yes. So you can recover accelerations via this like there would just be like ones and minus ones. Like if you wanted, so basically what you can do is you can get or you know this of your x's, but that is just to get accelerations. If you want some other features, it's going to be like you put a quadratic around your features, and that's a function of accelerations. So it's the coefficients are trickier, but they're never like so much like like my inverse dynamics, for example, is going to depend in some like nonlinear way on my acceleration, and that would have to be kind of put into the overall matrix. Yeah. Yeah, maybe we can start.
We have like a 10-step application problem. What about just using just a Google to like see could that work very well?
Yes.
Especially if it's like over some space that's not well shaped.
Yeah. So yeah. CM like sampling-based methods have been applied. I actually can give you a reference if you're interested. So I think like one really great example of this is like work called like STOMP out of CMU, like STOMP, and mostly it looked at for non-dynamical, for non-dynamical systems, just for like finding kinematic paths. But yes, cross-entropy methods are like you have to you have to be a little bit careful about with how you parameterize controls, because like typically with forward shooting, when you apply these methods, you just have like Gaussian noise, like you make perturbations to your controls via just like independent Gaussian noise. For direct collocation, there's a little bit care about how you propose your perturbations. But I think like STOMP is a paper that has is like very short, really great motivation. It does go over it, but it is a good idea. Yes, it's arguable. Like, yeah, it might be a more robust solution than the second-order methods, but second-order methods do tend to be faster at finding the solution, especially if you have good initial guess. Yes. And so actually combining the two of them, which I will talk a little bit about later, is like one way you can do it. Okay, well, maybe let's get back to it, where we'll talk about optimizing dynamics with contact and also talk about policy learning. And this part of the lecture is going to have more videos, so if you're fading, there'll be at least like some videos to watch. So dynamics with contact. Both shooting and collocation methods can be applied to control of movement without contact, and actually have seen success. So for like, if it's like for flying or driving or swimming robots, or finding collision-free paths for robots, both methods actually do tend to work well. But actually with contact, it's difficult to apply either method out of the box. You know, if you have, but this comes up a lot if you have, say, Leggett robots, or if you care about manipulation or interaction with the environment. It's very difficult. And the challenges are that contact introduces discontinuous jumps in your energy landscape. So you might have two states, like Q1 and Q2, that might be very close and similar to each other. But one very small change, if I just place a robot's hand on the table, that means the robot is able to apply contact forces, whereas like it couldn't before. So the dimensionality of F suddenly even changes between two time steps. And in some cases and like that leads to sharp discontinuities in the energy landscape. That's one issue. Another issue is that we don't actually have any gradient information or any feedback from forces that are inactive. So if the robot might be really, really close to the ground, but not actually touching it, there is nothing in our optimization landscape that tells us, well, soon, if you just place your foot a little bit lower, you would be able to apply forces and have all sorts of like actuation capabilities. There's no gradient information that's telling you that out of the box. So typically some of the solutions have been in the past to manually specify sequences of contacts, like all the footsteps for the robot, either manually or with some planning methods, or use demonstrations that just get you into the ballpark of the motion right away, or incorporate some specific motion structure, like specific state machines. And actually reinforcement learning is going to be one other example of dealing with this that you will see later in the class that actually has been quite powerful towards addressing this as well. So we'll have another option that is actually quite powerful. But the problem is, in all these cases, is that contact activity is an indirect function of state. But what if we make it a direct optimization variable like we did for the state? What if we directly optimize for contact activity? And that kind of brings me to some of the work that we've done in the past, where you start with a direct collocation problem, where you optimize for trajectories of all your joint angles of your robot, but also in addition, you optimize for these contact variables that are scalar, that basically pre-describe a set of possible contacts that you can have. And if this contact variable is 1, that means that foot or hand is in contact with the ground at a particular time. So you can see an example circled on the left. For the foot, at that initial pose, the contact variable might be 1. But for the right arm at time t, the contact variable might be 0 because it's not touching the ground. So I've highlighted all the contacts in red. And because these are contacts and poses are explicit optimization variables, you have to explicitly enforce consistency between them. The contact consistency and the dynamics consistency that we've seen before. Otherwise, you could just get trajectories like the robot just flying towards the goal. So this contact consistency, I don't want to go into too much detail on where it comes from, but very briefly, it comes from the complementarity conditions on forces. And basically, this, what it says is that when the contact variable for a particular limb is 1, it means that limb must be touching the ground and not sliding. And when the contact variable for that particular limb is 0, the limb is, like the palm of the hand or the sole of the foot, is free to move in space however it wants. And the dynamics consistency basically is this F equals ma that we've seen before, except we're going to assume that all possible contact forces we can have are always active. So the dimensionality of F and J of Q does not change. So the set is constant. Instead, to our optimization problem, we're going to have this, this penalty function that says if the contact is 0, we're going to have, for a particular limb, we're going to have very high costs on trying to apply that force. And if the contact variable is 1, you don't really have like a very high cost for applying it. So inside our inverse dynamics function, we're going to kind of have this soft nudge. And so what happens is basically the trajectory optimization. You can think of this as like a nested optimization. At the high level, you optimize for control sequences, and at the low level, you're finding U's and F's. And it's via these contact variables that high-level trajectory optimization guides this low-level inverse dynamics solver. It tells it, like, okay, I want contacts to be active or not active here. And at the end, we end up with a problem that doesn't have any discontinuities due to contact, and always has the gradient. And in particular, can be solved with standard local optimization methods like the Gauss-Newton method that we've talked about. And on circa 2012 machines, it takes about 2 to 10 minutes, and surprisingly isn't that much faster these days because most of the effort was spent on GPUs and compute. But let's just maybe take a look at the example of how this optimization progresses to give you some intuition. Let's say we have some initial state, like the initial state of the robot here, and the goal is for it to be standing over the white crosshair target you see. Well, early on, what you see is the optimization is finding paths that are basically just flying towards the goal. And all the blue squares you can see, that indicates that it thinks the contact variable is on. So it's basically thinking that it's like, oh, it's pushing off the air and just flying towards a standing pose. So this is what I meant by the usefulness of inverse dynamics as a soft constraint. It allows you in the intermediate stages just to break laws of physics and entertain all sorts of infeasible possibilities. But later in the optimization, what we're seeing is that because of this constraint that contacts need to be touching the ground and not sliding, you can see it converging onto, or touching the ground, you can see it converging some contacts either going inactive or being attracted towards the floor. And in the late stages, because of the not sliding objective, we see that contacts actually converge to single points in time. And as a result of the optimization, you can see a motion that is getting up and kind of like is physically plausible.
Just a quick question. The fact that it would have pushed error at the beginning and later not does it, and it slides and then later not slides, is that the result of you explicitly changing some?
In this case, this was at explicit 3 stages, where, yeah, like kind of similar to continuation methods, you have some weight, you start with some weights being low, and you set them higher. In the recent results, it was actually possible to get away from these 3 stages, and I will show some examples where that's not necessary. But because this was just very early work, you know, we tried all sorts of things. Yeah?
So what's the difference of like gradually adding the constraint instead of like putting the constraint at the first step?
Instead of what? As opposed to what? Sorry.
As opposed to like when you are solving the optimization problem, you just put the constraint.
As a hard constraint, you mean? That limits the space that you can explore. So if you put it as a hard constraint, you always have to be finding, say, solutions that that are basically in the space of, like, in this space of solutions. You cannot entertain possibilities like just flying towards the goal at first. So this is what it allows you to do. Sorry, I'm not quite sure if that makes sense. Maybe another way to phrase it. Maybe another intuition is like similar to relaxation methods, where let's say for in integer programming, like you might always be trying to find, like, so your solutions are like integers, but you might be able to apply relaxation methods where, okay, they can be continuous variables in the intermediate stages, but then they move towards actual, like, towards integers. So, and relaxation methods can be maybe like much easier, like continuous problems might be much easier to solve. So this is kind of the intuition. So in general, the idea is you try to only softly enforce the consistency between various variables that you have. And it might result in a larger search space, but it's easier to explore possibilities in via the main idea of like adding these auxiliary contact variables. So maybe some of the other examples of what this can get you is a similar goal to what you've had before, just stand over the white crosshair. But if you vary the environment, you can see a number of different strategies that can come out from these optimization methods. So here we've allowed the robot, just like allowed forces that can pull, so the palms can pull and not just push. And we're seeing kind of solutions that actually end up doing like working well for all the various like gaps that you can have. You can also optimize, instead of standing at a particular orientation, you can flip the orientation and get kind of these handstand behaviors with all the right preparatory motion. Or I can place like a bunch of locations like where the hand should be and have a particular velocity and get kind of like a sequence of punches or kicks, like, and all the while, you know, the agent is keeping, or the robot is keeping balanced because, well, in order to keep making the kicks, it needs to be kind of balanced. Can also generalize it to non-humanoid morphology. So you can ask, like, how would this walking couch-like thing like go over a gap, and we're seeing a sensible sketch for the motion. You can also optimize for interaction with props. So let's say we add additional props and additional variables, saying that you can make contact with these props. By only specifying the final location of the box, we can get a trajectory that makes the character like come up to the box and place it. Because what happens in the optimization is, well, first the box just by itself flies towards the goal. But then the optimization asks the questions, well, in order to fly towards it, it needed to have some contact forces applied to it. Well, in order for it to have contact forces, it needed these contact variables to be active. In order for those to be active, the hands need to actually be touching the object. So it's kind of like the optimization sets off a chain of dependencies. And you can also look at multiple agents or multiple robots coordinating. And again, the only objective here is like on where the box should be. There's no objectives or no costs on the movement of what the robots should do. Or here, if the goal is just to have the top of the little agent reach a particular height, and there's no constraints or no objectives for what the big robot should do, we're still getting kind of like these climbing behaviors. And yeah.
In this like two-agent setting, are you optimizing over them as like one big system?
Yes, yeah, it's like one big system, so it's kind of like a hive mind, collection of agents. It's not decentralized.
It seems that the agent on the bottom has a tendency to touch the ground,
Mm-hmm.
even before it needs to climb up. Is there a reason for it?
So I think it's an artifact of this particular set of effort objectives that we've set. So we've had some regularizer that was saying, I also want my contact forces to be small, so I don't want to exert too much contact force. And what the consequence of that was it tries to balance all the forces. And so instead of standing on 2 feet, it is actually like under its model of metabolic effort, it's easier to just place, like sit, basically. So yeah, we can also apply it for hand manipulation, and it's exactly this kind of the same setup where you have now variables for contacts between the fingers and the object, and you can do various things like grasping at a particular orientation of a variety of objects, or manipulation, where the goal here is just to have the object rotate at a particular velocity around the x-axis or the z-axis or the y-axis. What we're seeing here, though, is one consequence of having these dynamics be as soft constraints. So as you can see here, it generally is a pretty sensible sketch of the motion, but like things look a little bit floaty, and might be breaking might be breaking the physics a little bit. And this is because that inverse dynamics residual, again, is just a soft constraint. And our trajectory parameterization, like we're optimizing for sequences of states that might be pretty far apart in time. So some of the intermediate states like might not be plausible. So there's like always a small residual. And this is in contrast to forward shooting methods where you are always going to get something that's plausible, but just might be a lot harder to get. Can try different robot hands, or you can even try multiple hands, kind of again as a hive mind, like you say, coordinating together to pick up an object. Or sorry, actually just wanted to check how much time, when does this lecture officially end? At 12:20? Oh, 12:30, okay. All right, cool. Yeah. The other thing I briefly just wanted to describe is you can also put more detailed models of, so I know the class is for robotics, but you can try other actuation models, for example, like muscles. And muscles actually have their own very detailed dynamics, which you can again write out the equations of motion for, and get more detailed agent behaviors or robot behaviors that actually then show you what are the actual muscles doing, and like how much are they activating and contracting. And this is a case, like you've asked, are these solutions unique? Here, for the case of muscles, they are actually not, because like you might be, like, am I just having very little effort right now, or am I contracting really, really hard? There's no way to disambiguate these two cases. So there's just additional regularizations you need to put in place to deal with that. And we can see that actually it does tend to recreate human walking patterns, both in terms of torques and kinematics. And we can just specify higher velocity and get detailed movements of running at 4 meters per second, or like walking on the moon gravity, or initiating gates, or stopping gates, jumping to various locations, or kicks again, or back kicks. I don't know. That one was, these motions were fun to generate. There's all sorts of things you can do. So I should bring up another example where you're asking, okay, do you have to just optimize for the states? And again, the answer is no. There's been a lot of also successful work that explicitly optimized for states, controls, and forces, and has done so as a hard constraint. And so one excellent example is the work of Michael Poza and Russ Tedrick in 2012. They've done really detailed models of, like, let's say, an ostrich-like robot running that were actually, there was no residual, so you could actually like really deploy it on the robot. So it's another case. I unfortunately don't have videos for it, but it does look great too. So this, yeah.
So all these videos that we've been seeing, you have to be very careful how you define the cost function. And did you use any form of human demonstrations?
So the cost function, you basically, the big thing was, again, like for motions like moving the box around, you did not want to create any hint or like informative costs in this case. So the costs were like around satisfying the goal, which is like I want the position of the body to be here, like which was expressed as a quadratic. Some metabolic energy expenditure, like I want to minimize sum of squared of torques. I believe like Pieter kind of talked about that, and minimize sum of squared of maybe contact forces, so some measure of effort. And some so we've had general regularizing objectives on the basically the pose. So I want the default pose of the character just to be kind of like close to a standing pose. This was just something to, make sure I don't do just rest in various poses like that. But there wasn't a kind of a hint towards what I should be doing with this box. We wanted that to come out of the optimization. And no, there were no demonstrations here. Again, this was very explicit not to see what you can get de novo, because in some cases you might not have, for a robot of a weird morphology, you might not have that big walking couch. You might not be able to get demonstrations for that, right? And lots of robots are weirdly shaped. So yeah, for trajectory optimization, I've seen this with general approach, pre-automatic. It solves an optimization problem to get each clip of this motion, or an open loop trajectory. But there isn't really any learning or reuse in these solutions. And it also cannot deal with unexpected events. So we're going to be, instead of looking for just optimizing for clips, we're going to try to look at how we can use these methods for finding feedback policies instead. And one of the ways in which you could, and that brings us to this, and one way you can really apply it is Pieter talked about model predictive control in the last lecture. And that would actually be a really perfectly sensible and I think a very nice way to be finding control policies with feedback, where I optimize, I use my trajectory optimization to plan for the future. I take the first step, act in the real world. I might find myself in a new state, but then I just keep replanning. I think this is a very good approach to it, and I think Pieter covered it pretty well. So I'm going to skip it, not because it's a bad idea, just because he already talked about it. What instead I'm going to talk about is this approach that was alluded to in the last lecture for how we can use collocation to get a feedback policy. So to make sure we're on the same page, the policies we're going to be considering is just some deterministic function that maps from states to our controls. And what we're going to do is we're going to, in the case of shooting methods, optimize for policy parameters that, when rolled out forward, are going to minimize the cost. But again, we're going to have these poor conditioning issues around forward shooting. So one way you can try to make this problem easier is to learn from demonstrations, where policy learning just becomes a supervised learning problem. Like maybe another names for it, like behavioral cloning is a term that comes up a lot to describe this. But where I basically have a lot of demonstrations of trajectories and controls, and I just try to fit a policy to recreate those sequences. And where can the demonstration come from? Well, it can be coming from human demonstration, but we can also use our trajectory optimization to arrive, to generate arbitrary amounts of this demonstration data for us. And that's how we're going to approach this problem. So we're going to propose a set of tasks and use a trajectory optimizer to solve a particular task. So let's say I'm starting in some initial state and I want to walk forward 3 meters, or I might have another task where I want to walk backward 2 meters. For each of these tasks, I'm going to run the direct collocation optimization method that I've from the first part of the lecture. I'm going to collect all the states and action pairs from these trajectories, and I'm going to fit a policy, like let's say a neural network, to recreate these. So then I would be able to generate all sorts of in-between motions that move to all sorts of, generalized to all sorts of in-between velocities. The problem, though, is that this data set of trajectories can be inconsistent or very difficult to fit. So we've looked at an example of generated like a flapping bird motion, and you can see degrees of freedom for both for the task of the bird just staying in the air. And one way to achieve it is just to flap very, very chaotically, and the other one is to kind of create these regular cyclic patterns of flapping. Both of them satisfy the task, but one of them might be a lot easier for your neural network or for your policy to fit. Like the one on the right might actually would be a lot easier to fit than this chaotic behavior on the left. The other issue is that the set of trajectories might be inconsistent. So depending on my random initialization, if I'm standing and I want to start moving forward, I might start walking with the right foot, or I might start walking with the left foot. And both of those would be equally viable. But a deterministic neural network will try to fit maybe both of these solutions and do something in between, which would not be a sensible interpolation. So that is why what we're going to do is we're going to make sure that our policy actually feeds back into the trajectory optimization problems. And the way we can do this is we can simultaneously optimize for this pose a joint optimization problem, optimizing for the policy parameters and this whole set of trajectories, where we have the traditional trajectory optimization cost, as we've had before, but we also have this additional term that will couple the policies and the controls. And so what it's going to do is it's going to, so one way, basically our trajectory optimization is going to propose us some controls, and the policy might propose something else. So we have this discrepancy, and or this inconsistency between trajectories and what the policy outputs. And the way we can reduce this discrepancy is we can adjust the policy, so just train it for longer, make it fit our sequences of U's better, or we can adjust the trajectories instead. We can adjust the U's to kind of start matching the behavior of the policy pi. And so the idea here is, again, you've added the auxiliary variables. Instead of just optimizing for policy parameters, we're going to optimize for policy parameters and a bunch of trajectories. And they can be inconsistent, but we're going to softly enforce the consistency between the policy behavior and trajectories. And again, that results in a larger but an easier to explore search space. Because again, your rollouts are not bound to, much like before, we weren't bound to satisfying laws of physics by construction. Now we're not bound to just trajectories that follow the policy by construction. And in practice, we can kind of decompose this joint problem into an alternation of just trajectory optimization problems. We can solve for each x independently with this additional quadratic that says stay close to the policy. There's probabilistic interpretations of this, like so if you know like work of guided policy search, this is basically same idea except you have KL divergence instead of just a quadratic. And a regression problem that is basically our supervised learning problem. And we alternate between these problems. And it can be done on multiple machines, but that's a little beside the point. And so what that gets us in the end is or policies now that we can interact with in real time. So the green is something that is a cursor that I'm just controlling interactively, and we have this flapping bird-like character that tries to track the target. Or we can make the viscosity of the medium or medium a little bit viscous, that's more like a fluid, and get this weird turtle-like creature to also track the target and track target orientation. And so again, even though we were doing trajectory optimization, the object we end up with is a feedback policy, is a closed loop policy that's like a neural network in our case, can be executed in real time. Can also use it for interactive control of bipeds. So here I'm controlling for this biped, and you can see the contact forces that are being applied as well. And so yeah, it's pretty responsive, or we can get like shorter bipeds and get like weird baby chicken things walking and tracking the cursor as well. Or weird couches again, now walking in real time. Or quadrupeds that move around or turn around. And so in this case, it was like maybe on circa 2014 machines, about 2 to 3 hours of training all the various trajectories. But in the end, is you get something that's real time, or a weird spider. We really wanted to make the spider go up walls to make it even creepier, but we didn't have time before the deadline. Oh, shoot. You can also try to deploy these on real robots, like making these biped robots get up, or with interactive policies, have it kind of, oh no, I was not expecting this to have sound. But yeah, you can get it to control it interactively, or the work that was done here at Berkeley, like control end effectors interactively of these robots and still have them be balanced. So yeah, that's all I wanted to talk about. If you have, still have some time, happy to take any questions that you have about any of this work.
One quick question. What's the time complexity like with respect to the dimension of the state space?
Time complexity in what sense? In solution?
To solve the trajectory optimization problem.
Again, I haven't looked at this work recently, although I'm trying to. But at the time, for those motions that you saw, it's like 2 to 10 minutes of optimization on.
Say if you have one hand manipulating something versus two hands manipulating something, does it increase?
It increases, but in general, the increase is close to linear in the dimensionality, because again, like we have the solution is a band, like the problem we're solving is a band diagonal system, so we don't have this quadratic or cubic explosion. and complexity. Yeah, any other questions? And again, also just wanted to say, so I think like reinforcement learning is another very good alternative to dealing with contact that you will see later in the course. Very relevant, but hopefully, yeah, looking at what inverse dynamics solvers do and what's actually happening inside a physics simulator was also could be useful for you. Yeah?
Then the policies you train at the end, were they contextual middle policies that you move the target around, and then like how many directions did you have to get the robot to move in before you did in general?
Yeah, they do take as input like the goal location that is explicitly given as an input to the policy. And the number of goals typically end up randomizing. I think we ended up, for those problems, about 5,000 random goals. That's kind of like where things start getting. I don't have like the plots of performance with respect to number of trajectories, but in practice, like depending on the problem, 1,000 to 5,000. So it's like on the order of thousands of trajectories that it starts getting competent. Yep.
So what are some of the open problems right now that you're excited about? And, like what isn't solved?
Well, one is these systems will still somewhat simplistic, and you need it to have the inverse dynamics model. So you need it to know this model and run a physics simulator, or like use a physics simulator. Learning these models from data actually, I think, like could be really powerful step. So then you would be able to deploy it, towards learning in the physical world. I think there's also opportunities for more complex and long horizon tasks. So here the tasks we're looking at were pretty short. It's just like I pick something up and I place it somewhere else. But like performing a long horizon, like a long-term sequence of actions, opening a door, opening a cupboard, then taking something else in, walking around, that is not something that is, I think like these methods, as you increase the time horizon, these methods do start to kind of like become harder to find solutions for. So they might basically, I think the main failure case is that there is a strong, because this is soft optimization, there's a strong appeal to cheat. So if you give it something that's really long horizon that requires making many steps, it'll just try to skip steps. So it's like, oh, like for like a tiny amount of time, I'm just gonna imagine that my the cupboard is opened, and I'm just gonna pick something from it, and I'm not gonna waste time like making a motion that opens it up. So it does tend to fall into these local minima. So I think methods that do incorporate learning and potentially operating at multiple time scales. So maybe I find a proposed trajectory at a very coarse time scale, and I do have a learned dynamics model for not just how to go from one literal state to the next, but how do I go from here to there. I want like a kind of like a coarser, like longer horizon model that will tell me, okay, this is possible. We'll figure out how, but it is. Versus me ending up over here on the ceiling is not going to be possible for sure. So then you can chain multiple optimization of multiple timescales, and actually multi-grid methods in the numerical methods literature have been one path towards kind of dealing with that. Which could be something interesting that hasn't really been explored in the context of optimal control for robotics too much. So that's another interesting opportunity. But basically, yeah, long horizon and more complex motions. The other is to try to maybe incorporate some hard, like for certain cases, for certain applications, you would need to actually deal with hard constraints, like for the case of, let's say, biomechanics, if you were try to ask the question, like we're generated movement at 1.5 meters, at 4 meters per second. If you ask a question, what's the fastest a human can possibly run? And so you just put the target velocity higher and higher. These methods are not going to tell you, okay, past a certain velocity it's just impossible. They're just going to cheat, like little by little, start breaking physics to succeed. And sometimes you don't want that. Sometimes you actually want realistic solutions. So actually imposing things as a hard constraint, imposing dynamics as a hard constraint, is another problem that I think is worthwhile to look at. Yeah. So that's just off the bat what I can think of right now. Thank you.